So I want you to imagine a massive, highly dynamic engine that covers a whopping 71% of our planet. Now imagine that this exact same engine holds literally 1,000 times more heat than our entire atmosphere. It's vast, it's incredibly powerful, and it absolutely dictates the world as we know it.
Welcome to this explainer. Far too often we look at a world map and we just kind of think of the ocean as this passive bathtub, right? Just sitting there between the continents. But as the data clearly shows, it is anything but passive. It's actually a complex, continuously moving system that completely governs our global weather, controls our food supply, and heavily influences major natural disasters. So today, we're going to map out exactly how this invisible engine works.
Okay, let's dive into this. Here's our roadmap for the explainer today. 1. The ocean's heat engine. 2. The global conveyor belt. 3. Upwelling and marine life. 4. The El Niño climate seesaw. And finally, 5. Supercharged variability.
Section 1. The ocean's heat engine. Surface currents.
Up at the surface, driven by the wind and the Earth's rotation, the Coriolis effect, we get these massive rotating water systems called gyres forming on either side of the ocean basins. On one side, we've got western boundary currents. Take the Gulf Stream in the North Atlantic, for instance. It is warm, fast, and remarkably deep. And the amount of heat it carries, it's almost unbelievable. We're talking the equivalent of roughly 1,300 times the total power capacity of all U.S. electricity generation. This single current is the whole reason Western Europe is 5 to 10 degrees Celsius warmer than it really should be at that latitude. Now contrast that with eastern boundary currents. Look at the California current. It's cool, it's slow, and it's shallow. And it's exactly why the Pacific coast of North America stays so remarkably cool and dry.
Moving on to Section 2, the global conveyor belt, deep ocean circulation. But what happens when we drop down below the surface? Well, the wind is no longer in charge down there. Instead, water density totally takes over the steering wheel. We call this thermohaline circulation. Thermo meaning temperature, and haline for salinity. Basically, cold water is denser than warm water, and salty water is denser than fresh water. So in the North Atlantic, the Gulf Stream delivers all this warm, salty water up to the high latitudes. As it cools down, it becomes incredibly dense, and it literally sinks right to the bottom of the ocean. This massive sinking motion drives what we call the AMOC, the Atlantic Meridional Overturning Circulation. Think of it like a vast, deep ocean river flowing right across the seafloor. Now, this global conveyor belt is definitely a marathon, not a sprint. It takes roughly 1,000 years for water to make just one full circuit. But here's the thing, it isn't invincible. Because it completely relies on salty, dense water sinking, a sudden influx of fresh water can actually bring the whole thing to a grinding halt. And we know this for a fact because it happened 12,900 years ago during the Younger Dryas event. Massive pulses of glacial meltwater freshened up the North Atlantic, reduced the water's density, and just stopped the deep water from sinking. The conveyor belt basically hit pause, and Europe was plunged into centuries of rapid cooling. Fast forward to today, and climate models show that continued fresh meltwater pouring off the Greenland ice sheet poses that exact same risk to this absolutely crucial system.
Section 3. Upwelling and marine life. The deep meets the surface.
So, what happens when those cold, ancient waters are finally brought back up to the top? That brings us to a biological miracle called upwelling. Along eastern ocean boundaries, when winds blow parallel to the coast, the Coriolis effect actually pushes the surface water offshore. It acts exactly like a giant vacuum. As that surface water gets pushed away, cold water from the deep ocean is sucked right up to replace it. In this deep water, it's dark, it's ancient, and it is absolutely loaded with nitrate and phosphate from sunken organic matter. When those deep-sea nutrients finally hit the sunlit surface, it's like throwing fertilizer on a lawn. They feed explosive, massive populations of phytoplankton.
To put that into perspective, just look at the real-world impact here. Upwelling zones cover only a tiny, tiny fraction of a percent of the total ocean area, yet they are hands down the most biologically productive marine systems on Earth. The Humboldt Current upwelling, right off the coast of Peru, generates an unparalleled volume of fish by weight. In fact, it supports the world's largest single-species fishery by annual catch, relying almost entirely on millions of tons of anchovies. And every single bit of it is fueled by that deep, cold, nutrient-rich water being vacuumed up to the surface.
Section 4. The El Niño Climate Seesaw, Walker Circulation, and ENSO.
Now, as you might guess, this delicate balance isn't permanent. Notice the stark contrast here between the two extreme phases of ENSO, the El Niño Southern Oscillation.
Normally, trade winds blow a massive 2-meter-thick pool of exceptionally warm water way over toward Indonesia. It just sits there, a solid 8 to 9 degrees Celsius warmer than the eastern Pacific. But during an El Niño event, those trade winds weaken, and that massive warm pool literally sloshes back east across the Pacific. On the flip side, La Niña is the total opposite. The trade winds kick into overdrive and push that warm pool even further west than normal.
Let's walk step by step through the domino effect of an El Niño off the coast of Peru. It's fascinating. Step 1, the trade winds weaken. Step 2, that giant warm pool migrates east, right towards South America. Step 3, the boundary between the warm and cold water, the thermocline, deepens. Step 4, because that warm water is sitting there like a heavy cap, the cold, nutrient-rich upwelling is completely suppressed. The vacuum is broken. And step 5, without those crucial nutrients, the phytoplankton die off and the entire Peruvian anchovy fishery completely collapses. It is an absolute ecological and economic disaster.
So, let me pose a question to you. If El Niño causes all these major disruptions, is La Niña just a return to normal? Are La Niña events simply the absence of El Niño? Well, the answer is a hard no. La Niña is actually an extreme intensification of normal conditions. Pushing that warm pool even farther west causes massive flooding in Australia and Indonesia, sparks severe droughts in Peru, and it even reduces wind shear over the Atlantic, which actually allows dangerous hurricanes to organize much more rapidly.
It's like this crazy global butterfly effect. Just a mere 1 to 3 degrees Celsius temperature shift near the equator completely reshapes the global jet stream through what scientists call teleconnections. During an El Niño, you can simultaneously get severe flooding in Peru, massive droughts and raging fires in Australia, and somehow a notably mild winter all the way up in the U.S. Northeast. The atmosphere is totally interconnected, and this one tropical temperature anomaly ripples across literally every inhabited continent.
And that brings us to Section 5, Supercharged Natural Climate Variability.
So what exactly happens when we take these historical, natural cycles and lay them over human-driven changes? Well, we see a rapidly escalating trend. In 1982 to 83, we saw catastrophic floods and $8 billion in damages. By 1997 to 98, that skyrocketed up to $45 billion in damages, and severe droughts triggered fires in Borneo that released a staggering 2 billion tons of carbon. Just let that sink in. Then, the 2015 to 16 event saw the worst mass coral bleaching of the Great Barrier Reef to date. And the 2023 to 24 event? It just shattered global surface temperature records month after month as the El Niño rode on top of an already artificially warmed ocean.
This quote really hits the nail on the head and captures our core takeaway for today. The El Niño cycle isn't some externality. It's not just a separate issue we can manage away from the baseline climate. Yes, it is absolutely a natural mode of variability, but its consequences are being violently amplified, literally supercharged, because the baseline temperature of the ocean has been fundamentally altered. Think of it this way. The natural swings of the seesaw are hitting harder because the whole playground has been lifted up.
So I want to leave you with this final thought. We've seen how the ocean acts as an incredibly powerful invisible engine, governing heat, nutrients, and weather across the entire globe. But as those background ocean temperatures relentlessly continue to rise, how exactly will humanity adapt to a world where these essential, natural cycles become unnatural, supercharged disasters? Thank you so much for exploring the mechanics of our ocean with me today. Keep learning, stay curious, and I'll catch you in the next explainer.